All right, welcome back to channel, and this is a section about playing with some cubic graphs with external resources in House of Graphs. And I'm going to show you a notebook, quickly explain that, and show you how to import this data. And I think this is a kind of useful stuff if you really want to generate or just pick up random cubic graphs with a certain type of constraint. So the data I use is from House of Graphs, and choose 36 nodes with the girth is exactly is no less than 7. And because it's cubic graph, so it's also called 3 regular. So each vertex has 3 edges that connects to it. And I believe this graph is not directed. So each edge is, there's really no directions connect to that. And you can, for example, take a look at the node 14 here. It's a vertex here, and you do have 3 edges from like shooting out from that vertex. Or you can think about it, there are 3 edges, 3 rows coming into this vertex, and this properties applies to all the graphs and all the vertices. And this is usually a very difficult problem, and takes really large effort to generate all these non-isomorphic graphs. So which means for these 2 graphs, you really cannot permute the vertex of this graph and apply that to this one. So this is extremely time consuming to compute in general cases. So I'm really appreciate people using their computer power source to create these data sets. And if you want to do that in Wolfram language, you don't have to do that from very beginning. You just go to the website and download data. If you click this one, you actually will have a file download to your computer. And this is the file, and I use this command. It's going to set directory, notebook directory. So I just put this file in the same folder as this notebook. So I can just import it directly using the file name. Instead of using import graph6, because this file is quite large. So what I do is use more low-level like stream. It's called open read. Open read is something like standard IO, and in C++, you can import a stream of you can import a stream, and every time you read a line or read a word, you basically scan the element inside the file. So this gives you a very low level but a really fast connection to import the files one by one. The issue with the original import is though the graph6 format is supported, but if you import that directly, the Wolfram will actually convert to this type of graph, which takes a lot more space to store than a pure graph6 stream. So without further ado, let's just load this stream and start to read. So you can definitely have better encoding scheme for that, but in this case, I just use a new tabular feature that actually handles this large data set pretty well. And it takes about like 70 seconds to load everything, and use about 10 gigabytes of RAM. So you can definitely make it better with the function compile, but on my machine with 32 gigabyte RAM, I don't really have issue to accommodate everything inside my RAM. Okay, so we can see this is the pressure, memory pressure of the system. So even though this can be improved, but it seems fine with my current system. And let's go back to the notebook. So here I wrapped everything with once. So every time if you want to just rerun the whole thing, but you don't want to re-import the data, actually it won't run for you, because the once make sure it only run exactly once in the current session. So this is really useful if you usually want like evaluate notebook features. So the most time consuming part will not be triggered every time you do that. So the next thing is simply sort of the playground that I want to take a look at how these graphs look like. So the tabular thing is actually very efficient. So if you just grab tab here and just load the tab, you'll see this is the exactly content inside the tabular. Of course, you see there are lots of prefix that shared, so you can't do actually prefix sort of compression to save a lot of memory in for this type of data. Or you can do that after you expand it into adjacency list. So this is actually used in Wolfram data repository for a different data that I recently uploaded. For example, let's go to data repository, and all unlabeled cubic graphs of order 18 with girth 3. This is data I uploaded from the regular graph database by Marcus Meringy. So this one use prefix data compression technique based on that website, and I show you how to decompress the data and convert it into graphs in this web page, so you can download it for free. And there are some other discussions for that. So if you want all the source code about it, you can just download this file. And for this one, I probably won't upload it because this data is kind of huge. Even after compression, it's still like 200 megabytes. So it's better for you guys just to download from this website. Okay, so this is all the data that you have. And there's a function called import string. Import string actually does have a support for these data. Say, let's just copy this one. Let's see. Okay. And convert into graph 6. Graph 6. So you immediately can run this command and convert this weird string into a nice graph. Okay. And the next step we do is let's run this part. I will show you why I need all edge here. And say I want to run some random graph generators, and all the graph must be cubic and have girth at 7. So this is something I do. First, I pick up a number from between 1 to sort of 95 million, because that's the length of data. That's all the data is proven for with this property and curated in the data set. And I picked like 9 numbers for that. So that's why I have 9 graphs here. Okay. And then the graphs will be stored in this variable, and after it's stored, I use partition to make it into 3 pieces. So after you put a list of say like 9 numbers, and partition to 3. So this is basically 129, and you do partition, and it's 3. Okay, and then the last step you put into either grid or graphics grid. So you will have a nice like 3x3 grid. I'm doing the same thing here, but just for the graphs. And for each graph, once I import it, the import string function does support graph options if this item is either sparse graph or graph 6 for this particular data type. So it actually gives you kind of syntax sugar. You can inject these options into the import string. And after that, you simply using a graphics grid to make an image with 700 pixels in width and height. And just zoom back. So you can see these are quite nice graphs. So I changed embedding. So by default, it uses Spring and either like a spring and electric particle type thing. It's basically using column force or the spring force to place these vertices on plane. So here I use a different. It's called a gravity embedding. I think it looks slightly better than the default option, and everything looks quite neat in this chart. And then you can put a vertex label and place name. So with name itself, it just put numbers around these vertex. But you can choose place center, so these numbers will be sitting inside the centers of the graph of the disks. So this is basically the options I added into these graphs, so make it look a lot better than the default one. And then I use the this stored value, and I can actually extract these graphs directly, because in the output they are actually an object, controlled by the graphics grid. So it's graphics, and this is a graph. So you can see if you click the object, the color of the framework or the framed part is different. So this is a graphics, and this is a graph. Okay, and so this is the first item in this graph. So now you can just play with it and generate like interesting random graphs by yourself. Okay, it's quite efficient. You probably see it, runs for 1 second because it's using the graphics grid to align the stuff in the grid. But actual computation is really on the fly, because it's just generate integers and read these items from the list above. Okay, so I basically inject this variable inside this place. So eventually it only stores the graphs instead of the graphics object. Okay, the next function is simply a playground that I usually test for the new graph that I have. For example, you can take a look at the documentation here for the new data that I added to the function data repository. So centrality is usually the properties I'll play with. So what it does is called the betweenness centrality. What it does is you randomly pick two vertices on the graph, and because this is a weightless graph, you only count the number of edges between them, so sort of the length of the path. So if for all such pairs, if some of the vertex occurs more frequently than the others, then the circle will be larger. So the more formal definition is simply documented on the documentation page. So this is simply my verbal explanation of the first sentence in the documentation. So it's the more common vertex show up in the shortest path of other pairs, the larger the disk is in my graph. Okay, so in this case, every disk is the same because they are simply labels. But with centralities, this is sort of programmatically controlled by this option. So it assigns a different value for each vertex. And indeed, the size will depend on the centralities. So this is simply a visual check. So I don't have any theory behind why this one look like that. But if you have a lot of graphs and run it, you probably find a pattern for the centralities. So this is something probably a hot topic in random graph theories nowadays. I don't really think this type of thing can be done without the help of computers. Of course, if you want to close the form of maybe the distribution of the centrality when n is large or something, probably you can use Poisson distribution or some theory to get close the form. But it's always nice to have some experiment done in software to help you identify at least very qualitative pattern in the centralities. And the other thing that I play with is what kind of edge that I can add into the graph so that the girth is still, I would say, the girth is like still larger than 7. It should be at least the largest be or it contains the largest cycle, the largest cycle is 7. I think it should be this way. Okay, so if you add one more edge into the graph, usually you cannot do that because if you for regular graph we have like 36 points, and it's cubical graph, so the number of edge is fixed. It's 36 times 3. That's 108. 108 is divided by 2. That's 54. So you can really not add an edge to make it regular again. So this one is sort of like I only take about like the girth or the cycles. I don't really care about indeed this is the smallest circle. It is of length because I do check the girth of the of the new graphs that I do. What I check is how do I know this is the right graph? I actually did lots of random testing, so this is when actually pops up. So lots of a graph, if you add one edge, the girth will be 6 or 5 because you kind of have add something, so suddenly you have a really small cycle. But in my case is using this function to test this graph and try to add one possible edge in that. So this is the function that you need to use. Is first all edge. All edge is simply n choose 2, 36 choose 2, because the odd edges, once you have everything connected, it's complete graph. Complete graph is simply you have edge between all pairs. So this is all the space, and this is the complement edges. That's from my graph, and I extract all the edges or the pair of vertices and sort them by small to large. So each vertex is say 1 connect 2, and it won't be like 2 connect to 1. Okay, because this is sort of like kind of random. You really want to make sure that all the edges as a small number connect to a larger number. And once you have that, this is all the complement edges you have. And then you just map the girth of the graph that's to all the additional edge. And if the girth is 7, I think simply terminate the operation and catch the edge that I should add. So in this case, what it means is if I have the graph and append this 12 to 22 edge, so it's no longer cubic. It's no longer cubic anymore. Okay, it's not regular, because before you add anything, every vertex has 3 edges connect to it. So of course for 12, you have definitely 4 edges connect to it. To visualize whether it still indeed keeps the smallest cycle, you can change the embedding. I feel like this one is a good embedding for this type of graph. So it does change the shape from this kind of ball, hairy ball-like thing to this more structured items. Here, you can also add a vertex. I think a vertex size. Let's try 0.1. 0.1 here. Oh, okay, to reload this guy. Okay. So in this one, you can check some of the loops you have here is from like say 1, 3, 8, 17, 12, 5, 2. It is 7 because we have 7 elements, and maybe you can take a look at 8, 18, 21, 14. Then you probably can do that, but its girth is only about shortest cycle. So 1, 2, 3, 4, 5, 6, 7, 8. Oh, maybe this guy is like 8. So anyway, so you do have okay, 8 is fine because the smallest cycle is 7. So it simply means you can't find anything like 6 or 5 in this list. And it looks, if you just keep eyeballing these cycles, you can definitely find everything is at least 7. Okay, so this is the sort of the playground and discrete calculus part that I'm kind of interested in and play with it from time to time. If you have questions or ideas about that, you can leave some comment in the comment section. Okay, see you next time.